Hello students, today we're going to learn section 3.2, Exponential and Logistic Modeling. When you see the word modeling, you will be dealing with word problems. So we discussed exponential and logistic functions back in 1.3 when we went over its graphs and its characteristics. So this is an exponential function when you have a variable in the exponent. Alright, so let me just go over all of this with you. When you do these word problems, you need to understand what each variable represents. So when you do the word problem, you could just substitute the value wherever it belongs. So y is equal to the new amount, a is equal to the initial amount or original amount, and b is the base. Now b will either be 1 plus r, that's called a growth because you have a plus, or it's 1 minus r where it's decay. R is the rate. You will usually see a percentage symbol, and X is the time. So again, you need to know these variables to break down the word problem so that you could put it into the equation. Now there's a special type of exponential growth problem. It's called bacterial growth. It's when you see the word double. So the base is 2. When you see the word double, that means the base is 2. And again, you could see we keep the same format. If you see the word radioactive decay, half-life, the B is now 1/2. This problem deals with when, let's say, there's radiation in someone's body and they want to know how long it's going to take for it to disappear. They're talking about half-lives. So B is 1/2, A is still the same, Y is still the same, but now this exponent, it's going to be X over K. K means the half-life, and again, X is the amount of time it takes. So this is Y equals A times 1/2 to the X over K power, where K is the half-life. Alright, some other terms you're going to see. You're going to see this E. This E is what you call the natural number, and it's approximately 2.718, and it continues. E is similar to pi. Pi is the circumference of a circle to the radius, and that's 3.14159, and it continues. So E and pi, these are what you call transcendental numbers. So a transcendental number is a symbol that represents a value. So instead of writing 3.14159 and it continues, we have a symbol for it. It's called pi. The natural number 2.718, I think it's 1227, it continues. Instead of writing this number down, we have a symbol. We have E for it. So again, E and pi are what you call transcendental numbers. Alright, in example 1, it says determine if the function is an exponential growth or an exponential decay and find R. So to tell if it's a growth or a decay, you have to check the B term. Okay, you have to check this B term. Alright, so let's take a look at part A. Part A, we have P of t is equal to 4 times 1.018 to the t power. Well, B is 1.018. So since B is more than 1, because if you add anything to 1, it's going to be more than 1. So since B is more than 1, it's an exponential growth. Alright, so now to find, so we did the first part. We said it's an exponential growth. To find R, let's just use the formula. B equals 1 plus R. The reason why I'm using 1 plus R is because this is a growth. So I just substitute B is equal to 1 plus R. We know what B is, it's 1.018 equals 1 plus R. We're trying to find R because that's the second part of this question. Find r. Well, we just subtract 1 on both sides. We have 0.018 r. And when they want r, they want it as a percentage. So remember, when converting percentages, you move the decimal point 2 times to the right. So now this goes 2 times to the right. So r is 1.8%. All right, so now let's take a look at g of t. G of t here, g of t is equal to 7 times 0.05 to the t power. Well, b is located underneath the exponent, that's your base. B is 0.05, so that means that this must be an exponential decay. Because again, b is less than 1, so it has to be decay if it's less than 1. So we said it's an exponential decay. Write down the formula b equals 1 minus r because we said it's a decay. Substitute 0.05 into b. Bring all the other terms down. Subtract 1 on both sides. We have negative 0.95 equals negative r. We multiply by a negative on both sides. So r is equal to 0.95. And then again, to find the percentage, you have to move the decimal point 2 times to the right. So the rate is 95%. All right. Here is example 2. It says to write an exponential function from the given information. Y equals a to the bx power. So here's what they give us. They give us the initial value is 52 and increasing rate equals 17%. So the initial value, that's what a is. That's what we discussed earlier. Again, know what your y, a, b, and x are. So a is 52. Increasing rate, r is 17%. So if it's an increasing rate, we know we're dealing with a growth. So a is 52, increasing rate is growth, r is 17%, move the decimal point 2 times to the left. So it's 0.17 is the rate, because when we use it in a formula, it has to be in decimal form. So in order to make percentages into decimals, move the decimal point 2 times to the left. We have our a, we have our r, and our b, well, we're going to find out what b is. B is going to be 1 plus r because increasing means growth. So this is 1 plus r, which is 1 plus 0.017. I'm sorry, 1 plus 0.17, and b is equal to 1.17. So we have the a, we have the b, and we have the r. Now we can write the equation y equals ab to the x power. So there is a, b, and that's it. So y equals 52 times 1.17 to the x power. You might see this written as, I prefer to write it like this. Because sometimes if you put a multiplication symbol, some people might think it's a decimal point. I prefer to write it like this. Okay. This is how the book wrote it. I prefer it this way. But either one will work. All right, here's part B. Initial value is 5 and decreasing rate is 0.59%. So initial value, that is A. R is equal to 0.59%. Convert percent to decimal. Move this 2 times to the left. We have now 0.0059. It's a decay because it's a decreasing rate. So the base for a decay is 1 minus r. So we have r, 1 minus 0.0059 is 0.9941. So if you notice, the base is less than 1. Since the base is less than 1, we know it's a decay. We have our A, we have our B, and now we just substitute it into our equation. A, B. And again, I recommend to write it like this, so you don't think that this point is a decimal. It's multiply. Okay, I prefer to write it like that. All right, last one. For example 2, part C. We have the initial mass is 17 grams, halving once every 32 hours. So halving means it's a half-life. This is initial mass, so that means A is equal to 17. That's a half-life. K is now 32. Half-life means the base is 1/2. We discussed that earlier, and now we just substitute all these parts into our formula. So y equals 17 times 1/2 to the x over 32. And again, so we don't get mixed up with this multiplication symbol, I recommend to write it like this. Okay, so again, I prefer to write it like this so we don't get this multiplication symbol with mistake on it being a decimal. All right, so now let's talk about the logistic function. So remember, we discussed a logistic function just the last lesson. So we discussed the graph. We discovered that there's going to be 2 horizontal asymptotes. So logistic function means that there's a certain quantity that it's not going to go over a certain amount. It's going to approach it, but it's going to stop growing eventually because it's going to get closer and closer to this value. If you see it decaying, it's going to get, again, it's not going to get lower than 0. It's going to get close to 0, but it's not going to go lower than 0. So logistic functions means that there is either going to be a ceiling or a floor. Y equals c over 1 plus a e to the negative x. A is our initial. C is now our limit to growth. So that's what C is. It's right here. It's this upper horizontal asymptote. So the growth or decay eventually stops. And that's what I was saying. You're going to have horizontal asymptotes. All right, in example 3, it says Will Rogers Middle School has 1,200 students. 4 students start a rumor, which spreads logistically. So when they said logistically, we're thinking about this function. All right, so we have this function. S of t, they gave it, this is given. S of t is equal to our limit to growth over 1 plus 39 times e to the negative 0.9t. So all we do is we find out what these numbers mean. So it says 1,200 students. So that's our limit to growth. That's the maximum amount of students we have. It's 1,200. So it's going to stop at 1,200 students eventually. The rumor is going to get to 1,200 students eventually. And then all we do now is answer part A. Keep in mind, when we say t equals 0, that's your first day, the beginning day of when the rumors started to spread. Okay, so how many students have heard the rumor by the end of day 0? Well, that's t equals 0, so substitute 0 where we see a t. So this is 1,200 over 1 plus 39 times e to the negative 0.9 times 0. All of this is 0. So any number to the 0 power is 1. So you just have 39. So the first day, you're going to have 30 students would have heard the rumor. So 30 students heard the rumor on day 0. That's your beginning day. Part B, how long does it take for 1,000 students to hear the rumor? Well, 1,000 is now the new amount. So 1,000 goes in for y, or S of t. So we have 1,000 equals new amount. Okay. and we have y equals s of t. So to figure out the solution, just find out where this will intersect. So y is equal to 1,000, right? That's what that is. Y is equal to 1,000. So that's a horizontal line. And when you graph this into the graphing calculator, you will get this. You get a horizontal line and your logistic. So what you're going to do is you're going to find out where they intersect. Okay, so I typed in y equals 1200 divided by 1 plus 39e to the negative 0.9x. And I put in my second equation, y equals 1,000. So remember, whenever it's y equals a number, it's a horizontal line. So this is what you're looking for. You're looking for this intersection. So go to second calculate, and now go to intersect. And you're going to do this a lot in calculus. Okay, to find the intersection, your first curve is this logistic function. You want to be to the left of this, you just want to be to the bottom of this intersection. Okay, and so that's the bottom, hit enter, and then now you're going to surround any intersections. So look what I did. Here's the second function. Hit enter. So what I did was I surrounded any intersection between this graph, and it's going to locate it right there. Hit enter. And now it says the intersection is going to be 5.858, comma 1,000. So remember, x represents your t. So it will take 6 days, because it was 5.858, so we'll just say 6 days for 1,000 students to hear the rumor. All right, so that's example 3. Let's move on to example 4. So example 4, we're talking about exponential functions again. So it says the 2000 this is the year. So the 2000 population of Las Vegas, Nevada was 478,000 and is increasing at a rate of 6.28% each year. At that rate, when will the population be 1 million? So when you're thinking of this problem, it says when. So when is our time? That's our x. So we're looking for x. So let's label everything. So this is what we have. So we know y is equal to 1,000. That's our new amount. At what rate? At that rate, when will the population be 1 million? So that's your new amount. A is your initial amount. We said that. In the year 2000, it's 478,000. That's your initial amount. B is 1 plus r, just like always. The reason why I'm choosing 1 plus r is because this word increasing. The word increasing means it's going to be a growth. The rate is 6.28%. So I wrote that down. Convert percent to decimal. Find the base. It's 1 plus r, so 1.0628. So now we have enough information to find out what x is going to be. So that's what I did. I substitute 1,000 for y, 1 million for y, 478,000 for a. We already found b to the x power. Now, whenever solving for a variable in the exponent, you have to log or take the natural log on both sides. That's the only way to solve it by hand. So I'm going to show you how to do it. So what we're going to do is I'm going to get x by itself. I'm going to divide by 478,000 on both sides. So that reduces to 1. 1 million divided by 478,000 is 2.092 equals 1.0628. The next thing you're going to do is you're going to ln both sides. You're going to log both sides. So I'm going to put ln on both sides. Once you log both sides, there's a property back in IM3 or Algebra 2 where you could take the exponent and put it in front of the log. Now that the exponent is down to the base, we can now solve for x. So we have natural log 2.092 equals x times natural log 1.0628. To get x by itself, we just divide by whatever's next to x. So that reduces to 1. So we have roughly 12.12. So x represents the time. So it's taking 12 years. But it asks when. When. Not how many years it's taking. It says when. So since we started this problem in the year 2000, add 12 years to 2000. So it says the Las Vegas population will reach 1 million in the year 2012. Whenever doing word problems, make sure you answer the word problem in a complete sentence. Okay, so that is example 4. So let's take a look at this here. Example 5. It says the half-life of a certain radioactive substance is 65 days. So the half-life is 65 days. There are 3.5 grams present initially. So Y is new amount, A is 3.5, initial, right here. B is 1/2. How did I know it's 1/2? Because we're dealing with a half-life problem. So half-life problems, I said B is 1/2, X is time, and K is 65, because K represents the half-life. So it says express the amount of substance remaining as a function of t. So this is what we do. Y equals 3.5 times 1/2 x over k, but since they want it as a function of time, this is f of t equals 3.5 times 1/2 t over k. Remember, this is our base, that's the initial amount. So in example 5a, that's all they wanted. They wanted the function as a time of t. All right. So now part B, it says when will there be less than 1 gram remaining? So since this is the decay, what's going on is as time goes by, the amount of radioactive substance is decreasing using half-lives. So again, it says when will there be less than 1 gram? All right, so let's take a look at this again. The new amount is 1. A is the initial amount, 3.5. B, we already said it's 1/2. X is time. Half-life is 65. So all I'm going to do is I'm going to substitute all these values back into this equation or this equation. It's the same. So 1, 3.5, 1/2, 65. We notice that there's a variable in the exponent. So what I have to do is I have to log both sides. I have to divide by 3.5 on both sides. This is now 0.2857 equals 1/2 to the x over 65. Now that we cannot move this 1/2 because it's attached to this exponent. So again, whenever you have a variable in the exponent, what do? That's right, we have to log both sides, or natural log, same thing. So we natural log both sides. That means now I can move this to the front. Okay. So now I divide by log 1/2, log 1/2. That reduces to 1. All of this is equal to 1.807 equals x over 65. Multiply by 65 on both sides. So 65 times 1.807 is approximately 117.48. So it says when will there be less than 1 gram remaining? So it will take 117 days, I should have said approximately 117 days, for the radioactive substance to be less than 1. Complete sentence because it's a word problem. All right, that's it for today. Have a good day.